Hello everyone, sorry for the late post of the video. My microphone stopped working. And then I actually got, a friend came over last night and fixed it, but it was done at like 11:30, 12, and I didn't want to make the video then, so my microphone is working again, so I can make the video. So before we get into the PES PowerPoint, I want to talk about the ionization exceptions, and I'm going to post this PowerPoint also on Google Classroom, so before you might want to stop the video now and download it on Google Classroom. So on Friday we learned that ionization energy is the energy needed to remove an electron from, they have to be in the gas form, but either an atom or ion, okay? And then we also learned the trend is that it increases as you go across a period, because as you go across a period there are more protons, and this is the wrong there, oh well, therefore a greater effective nuclear force. So, this is also a typo, wow, I'm doing great today, you must use more energy to remove the electron. So again, because there's more protons, they pull harder on the electrons, and it's harder to remove them, so you have to use more force. And obviously you can fix my typos on the PowerPoint. So there are four exceptions, but they follow the same rule, or they follow the reason is the same. So if we look at as we go across, this is period 2 here, we see an exception here where here's beryllium, and then it goes from 899 to 801, and that's a decrease actually as you go across. So we need to explain that exception. And there's another exception. You'll notice between nitrogen and oxygen, it goes up. So after B it goes up, to C it goes up, to N it goes up, and then when it goes to O it goes down. And we have to explain that exception. So why is that? So if we look at these, so we're first going to explain the difference between BE and B and that exception. And if we go back, you'll see this. We're looking at this exception here. You'll notice the reason why B has a lower ionization energy than BE, and notice I didn't write anything, so you're going to have to type this in. Or write it down and then type it in, because I want you to learn sort of how to listen and write at the same time. Why? If you look at the electron configurations, it's easier, and remember, B is further, or it breaks the trend, it's further to the right. B is easier to move the electron from, because its last electron that it removes, and it always removes the one that's furthest from the nucleus, is the 2p. In BE, it's the 2s. And the 2p is further from the nucleus than the 2s's. So remember what I said, distance is more important? Because the d squared being, the d being on the bottom, and it's squared in the formula of Coulomb's law. So because in boron, the electron is further away from the nucleus because it's in the 2p, not the 2s, it's actually easier to move this electron, even though B has more protons, but it's easier because the 2p is further away than the 2s. And if we go back to the previous slide, you'll see that that's also true for magnesium and aluminum. Instead of being the 2s and the 2p, it's the 3s and the 3p. So that's that exception. So the next exception is the N and O exception. If we go back to the previous slide with the ionization energies, you'll see with N and O it's going up, and then between N and O it goes down. So why is that? So let's sort of try to explain that now. So here I have the orbital diagrams and electron configurations for nitrogen and oxygen. And the question is, why is it easier to remove an electron from oxygen than it is from nitrogen, even though oxygen has more protons? And the reason is in the orbital diagrams. If you look at nitrogen, nitrogen has 3 unoccupied, or like not completely occupied orbitals, whereas oxygen has 1 orbital that's completely filled. And why it's easier to remove an electron from oxygen from oxygen is that there's a repulsion force here. These two electrons they're both negatively charged, and we want to get rid of it. It wants to get rid of this electron. So since, like, to relieve the repulsion force between the two electrons, it's easier to remove an electron from oxygen than it is from nitrogen, because it has two electrons together in an orbital, and there's a repulsion force between them, which helps, you know, whatever's moving the electron take it easier, than because of the repulsion force of the two electrons being in the same orbital. It's easier to take this one away because they're kind of repelling each other to begin with. I just jumped back to the table. You see that this exception is also true for P and S, not as much. The drop is not as significant, but we go from 1012 to 1000, and it's for the same reason. This has two paired electrons, and that's not stable, or they repel each other. So it's easier to remove that electron because they repel each other, and there's a repulsive force. So anything that's trying to pull it away will sort of relieve that repulsive force between the two electrons in the same orbital. Okay, so now we're going to go to the PES. So there's actually lots of forms of spec. I can't say the word spectroscopy very well, so I just call it spec. We looked at one already, and we're looking at isotopes. Now we're going to look at one that helped discover, or it provides evidence for the fact of the orbital shell model, or the electron cloud model of the atom. Just like the other form of spec that we looked at, you don't have to understand the process, you just have to read the graphs that come from it, but I'm going to explain the process very briefly. So in the process, X-rays, which is a very large amount of energy, are blasted at atoms, and electrons at different energy levels are blown away from the atom with different amounts of energy. Okay? So, and then there's a charged hemisphere that bends the electrons, and the electrons with more kinetic energy bend less, and the slower ones bend more, and then the detector can tell how many of each electron, hit the detector with a certain amount of energy, and the binding energy can be then calculated, and then we get these graphs that show how many electrons hit the detector with what amount of energy. And if you look at the graph, this is for Scandio, and we'll explain why in a second. So this is the 1s electrons right here. So this is the 1s. So we can say this means 1 electron, 2 electrons, 3 electrons, 4 electrons. And notice that it took a lot. When they hit the detector, there was more energy there, again, because remember, they're closer to the nucleus, and notice that the energy on these graphs is going backwards. So, and then this is the 2s. I'm sorry, 1s. This is the 2s. This is the 3p. That's what am I saying? The 2p. It is like 7 o'clock in the morning. So, this is the 3s. This is the 3p. And then this is the 4s, and then I think that's the, let's do this again. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and then we go into the 3d2, which this is one of the exceptions that you don't have to know. Okay, but again, it says right here, you do not be able to need to understand or explain this process of how, X-rays are shot at it and they bend slower and whatever. You don't need to understand the process, okay? You just need to be able to read and interpret the graphs. Let's go to the next slide, which is giving me difficulty right now. Okay. So this is the PES of aluminum, and this will sort of explain it a little more. And again, notice that the energy is in the reverse direction. The higher energy ones that are closer to the nucleus are here, and the ones that are further away from the nucleus leave with less energy or less binding. So the left side here, he says, can sort of be considered the nucleus, and as you go farther from the y-axis, you go further out into the orbitals. So if you look at this peak is the 1s2, this is the 2s2, this is the 2p6, this is the 3s2, and that's the 3p1. And again, it's sort of very easy to follow the order, and they usually, as you say, this shows the photoelectron spectra of which element. The size of each peak represents a different sublevel, and the height of the peak represents how many electrons are in that sublevel or hit the counter during the process. So here we have two different spectra in the same graph, and one is black and the other is red. Okay, and I want you to take a second and see if you can determine which one is which one is represented by the black spectra. So you could pause it now and see if you can determine which one is represented by the black curves on the graph. So if we look here, again, we're only looking at the black curve. This is the 1s2. This is the 2s2, and then after the 2s2 comes the 2p, and you'll notice it has 1, 2, 3, 4 electrons. So that's 2 electrons here, 2 electrons here, 2 electrons here, and that's a total of 8. 4 electrons here. That's a total of 8. So the black graph represents oxygen in this case. Now see if you can determine which one the red is. So if we look at the red, and again you can pause it and do it yourself and see if you're right. This is again the 1s2. This is the 2s2, and this is the 2p1. So that a 2p2. I'm sorry, I can't even count myself today. So 1s2, 2s2, 2p2. So that's 2 electrons here, 2 electrons here, 2 electrons here. So that makes that, if you look at which atom on the periodic table has 6 electrons or atomic number of 6, and again, this is only with neutral elements, so we're assuming that they're neutral, the one that has 6 electrons is carbon. So we have one more question to answer, and then this lesson is over, and then you can do the last question on the homework, is, if you look at the graph, and we're going to go back to the graph in a second, you'll see that the black peaks are not in the same place as the red peaks. So let's go look back at the graph and try to explain why that's the case. So if you take a look, oxygen's peaks, the black ones, are more to the left than remember the left means more energy. Took more energy to remove. It's the binding energy, really. But this is the x-axis really should say binding energy. How hard are the electrons being held on to? You'll notice that the oxygen peaks are more to the left, or the binding energy is greater. Remember, the axis is reverse. And I bet some of you can predict the reason that is, or why they're more to the left, is that oxygen holds onto its electrons more. And if this was in class, I would ask, does anyone know why? Well, the reason why is that, again, carbon and oxygen are in the same period, or they go across, and oxygen has more protons, so therefore greater Zeph, or effective nuclear force. So the binding energy of the 1s electrons for oxygen is more than the binding energy for the 1s electrons in carbon, because oxygen has more protons, and therefore holds on to those protons greater. And you do have to remember that when you read these diagrams, the energy, or the x-axis, is in reverse. The higher numbers are here, and the higher binding energies, or the higher energies are here, and the lower energies are there. So that's it. You can now do the questions on all the questions on the homework, including number 7. So don't skip number 7 now, because I explained it. See you on Monday, which is tomorrow.